Okay, all right, so I think we are good. All right, guys, so welcome. So we have two more lecture, including this one, and then we should be able to just call it done for the waves and oscillations. Okay, so you might have heard from your friends or maybe, but we would like to discuss it officially here. The first exam, I'm not sure if you guys are okay. We might be able to discuss this when we have maybe more people in our class. But tentatively, it's going to happen on Saturday because it seems like it's hard to find like a fit during the weekday. So it might just pop up on the Saturday. All right, but we will discuss this in detail maybe before the break. All right, so let's dive into our material today first. All right, we have one more stuff that we would like to discuss related to the interference of sound. And this is called a standing wave. All right, so you probably will notice that the amount of slides in this topic is only like 3-4 slides. That's I know details. The reason is because we don't want to go back and deal with the detail too many times, but we would like to do something together in class to showcase that once you know the property of waves regarding the interference, then there is other phenomena that can happen as well. And that's what we're going to try to understand today. Good news. Toward the end, you will see that the conclusion of this topic is very simple. When I say simple, you guys kind of like know, like maybe it's not real, but the point is, it's really simple because you can kind of like throw away all those sinusoidal manipulations. You can throw away all those crazy and all this stuff and come down to just drawing some diagram or cartoon version of the standing wave physics. So you will see toward the end. But before we can get to that conclusion, we would like to discuss some theory. We kind of like familiar with that. So let's remind you a little bit where we are. We were talking about the interference of waves. And we already knew that everything based on a very simple rule, which is a superposition principle. And we keep saying that you can just add waves together and you call it done. Okay, simple. Whenever you have more than one waves, just add them up. Your job is done. So that's why the conclusion that we got last time was if you have y1 and y2, if you want to know what is the resultant wave, you just add them up. Your job is done. But last time, what we were looking at was the waves are in the same direction. They are traveling in the same direction. And then you get the in-phase and out-of-phase superposition happenings. And then you have a constructive interference. And then you have another one is a destructive interference, right? Remember what we did last time? And we had like a quick demo in class, sending out sounds from two speakers and try to observe the variation of the sound intensity, yeah? So there was like a it's sort of like a loud and quiet positions. Okay, and we did one of the exercise showcasing that in reality, what you really want to know is just the distances. And if you know the distances from the sources, then you can convert between the phase and the distance. All right, that is done. So we're going to do one more round today. All right, in the topic of standing wave. And what is that? So what we're going to do is we're going to go through this together. Hope it's fun. All right, and I will ask you to take a look at this. And at this moment, you should feel comfortable looking at this. Shouldn't be any problem anymore. If I write down first wave, it looks like a sine kx minus omega t. And I write down another wave as a sine kx plus omega t. First thing first, okay, if you write down something like this, we know everything about this wave. We know the amplitude, we know the wavelength, we know the frequency, we know the speed, and we know the direction by looking at the sign. So that means what I'm having right now is I'm having two waves that look alike, but traveling in the opposite directions. See that, right? One is traveling in the positive x, that's a y1, and y2 is traveling in the negative x direction. Nice. But because we have a superposition principle, which is super duper easy, if you want to know what happened as a result of these two waves combined, you said y, which is the next wave, is simply the sum of the two. Yeah? Okay, don't think too much because we only have one principle to rely on, and that's it. So all I'm doing is I'm just going to take these two and add together. All right. Looks okay so far. I'm just copy that lines down here. There you go. Haven't done anything yet. All right. But now, from this point, you just say, Bajan, can we do something else? Even though we don't want to deal with the detail before, but this time it looks symmetric except the sign. So I'm just going to recall this trigonometric identity that we kind of like briefly looked at it just briefly, that you have the relationship that you can turn the sum of two sinusoidal functions into a product. Okay, so I'm going to do this right now because it's kind of like end result is very clean. It looks clean in the end. So it's going to be twice the cosine of the difference over 2 and the sine of the sum over 2. I'm going to do that right now. Here we go. So I'm just going to keep writing 2. That's a factor from the formula. And then I have the cosine, the difference over 2. So what you have here is you can treat this one as A. You can treat this argument as B right there. Okay, so my first term in cosine is going to be the difference over 2. So I'm just going to take A minus B over 2. So it's going to look like kx minus omega t. And then subtracting out with that kx plus omega t. Everyone good? Divided by 2. A minus B over 2. Okay, I'm just going to follow this by another term in sine. So now it's a sum over 2. I'm just going to, actually, why don't I just put color on it? So it's going to be the sum of A and B. There you go. And then divided by 2. Here we go. All right. And what do you get out of this? Okay, first term, you can see, there's a negative sign. The kx disappeared. And if you look at the second term, it's a plus sign. So the omega t turns out to get canceled. So in the end, what you have is 2 cosine. You have twice the negative omega t divided by 2. So you get negative omega t out. The sine term, you have 2 of the kx divided by 2. You get back the kx. Now you don't care about the negative under the cosine function because it's the same sine, cosine of a positive or the negative numbers are the same. Yes. Yeah, coming from here. There you go. Okay, from the trigonometric identity. Yes. Okay, number 2 is right there. Yep. Okay, so what we have here is now I can just ignore that. 2 cosine omega t sine kx. All right, guys. What are you seeing? Woohoo. This is our conclusion. And that's kind of cool. I don't know if it's cool or not. Have you seen this type of equation before? Maybe not a lot, because as I said, this is the only spot in high school physics that, well, not the only spot, but is one of the few spots that you are dealing with a 2 variable function. So that's why you might not kind of see this. But what I'm showing you right now, that is a great sort of like a property built in. You see this? First term is purely on time. And the second term is purely on x. Ooh, we kind of like, it's kind of nice in a way. All right. And think about it. I saw this somewhere before. From the simple harmonic motion. right? We kind of know, I mean, waves is nothing more than just a series of simple harmonic motion, right? That oscillate in time, but sort of like in a different sort of like a step or a different time, starting time, think of it that way. So it's more of like, yeah, if I rearrange this one more round, I'm gonna write it as this, 2 sine kx, and then I pack this into like a one term, and then I leave the cosine omega t behind instead. Does this one look more like a simple harmonic motion now? Yeah. Better, right? And you already interpret whatever goes on in the front. That is your amplitude. So what does this mean? It means the amplitude depends on x. See that? And then when you think about it, now we can play around with this. If the amplitude of the oscillation depends on the position, there might be a position where you have 0 amplitude. Make sense? So that's something that probably pop up in mind right now. If kx is just multiple of pi, sine 0, sine pi, sine 2 pi, sine 3 pi, on and on, give you 0. So that will be the location where you have 0 amplitude. Wow. That is why we call this a standing wave. Because there are some points on the wave that the elements of the medium does not move. 0 amplitude, no oscillation. Does that make sense a bit? Yeah. So there are some points that there's nothing going on. Just nothing. It doesn't move. But on the other hand, you can do just a normal thing, of course, the maximum possible value is when sine kx is equal to 1, or the kx could be just pi over 2, 3 pi and a half, 5 pi and a half, on and on. That will give you a maximum. And that will lead you to the maximum amplitude. Wow. So what I'm doing over here is, it means right now, the amplitude of the oscillation among those values of x's are not the same anymore. There are some locations that there's no amplitude. This means the element don't need to move at all. And there are some locations that the oscillation happens at the most possible displacement, which is twice the original amplitude. Yeah. All right. So what we're going to have here is, let's coin in the name here. Anywhere that there's no oscillation, we call it a node. All right. This is probably not a node in computer, but it's just a node. And anything that's go violently, I mean, the one that has a maximum amplitude, we call it an antinode. There you go. All right. So how can we see this? All right. What is kind of like real or unreal, or what is what? So what I'm going to show you is this. I think the best way to learn about this, once again, is waves. So it never stops. It's moving at all time. So the best way that we can look at this is just look at the simulation. There we go. All right. So I once again call that ophysics.com. And once again, encourage you guys to take a look at this list of demo or simulator. It's very good, actually, so you can see things in motion. And the one that we're going to look at today is the standing wave right here. That's the topic of standing waves. It's in there. All right, here we go. All right, it's oscillating. It might look confusing at this point, but that's okay. I'm just going to start with something that is more familiar. I'm just going to get rid of the longitudinal wave. This is just a wave on a string, okay? And now when you look at it, I can create the oscillation mode that looks easy as possible, which is right here. Everyone agree, this is the simplest kind of waves that you can generate when you have a string fixed in your hands, for example, like this. You have this, all right? So if you just kind of like pick on it, it's gonna oscillate up and down. But this is the simplest case. But the reason that it has to go like this, because it has a fixed end point. The left end and the right end of this string has been fixed. It cannot move. So it's kind of like it's forced or it's restricted to be zero displacement forever. Make sense? So that's why for this particular setup, left end and the right end of the string going to be nodes at all times. You guys with me with it a little bit? Yeah, yeah. And the rest is just okay because you have to follow this restriction. You have to go from a node to another node to complete one full description of waves. But then you can say, Bajan, can you go on with the higher frequency? Yeah, that is another possible mode of oscillation. So for those of you that do music a little bit, you probably can observe this kind of thing with your like a string instrument, like a guitar or bass and everything, right? When you kind of like plug your string, then things start to oscillate. Sometimes if you plug it in the middle, it looks kind of nice up and down. But if you do a normal riff and everything, it's just going crazy on the string. This is another mode on it. But can you do more? Yeah. See, but the more the twist that you add it into it, the higher the frequency is going to get because the wavelength is getting shortened. Can you see that, right? So the more of the curve that you try to go from one node to the other node, then will create more waves that you have to put in the limited space. That's why it has to curve more. So the wavelengths get shortened, the frequency goes up. It's kind of like the relationship about that. Good. All right, so that is the idea with the string. But now what about sound, Ajahn? We already said sound is a longitudinal wave. So it's not going to go something like this. It's going to go differently. So let me put an air column instead. There you go. And this is what happened. But sometimes this open air column is just hard to imagine. I think the easier one is this one right here. One closed, one open. All right, so this one is cool. So when you have one sort of like ends of the column, when you say column, it could be like a tube, a tunnel, anything that has like a, a column of air in it. Right? It behaves like this all the time. So this is the way, here we go. So this one right here is just a wall. So this means the air molecule that's stuck on this wall will not be able to move, right? So your back is against the wall. So it's a guarantee that this ends, the closed end of this tube, will represent a node. Make sense? Right? Because air will not be able to move forever. So you won't get any displacement out of this. It's a guarantee, a node. But then on the open end, this one is the one that has all the freedom that it can do. So this is the part where things going to go all the way possible. There's going to be maximum amplitude on the open end. All right? However, imagine this whole thing oscillating in a longitudinal direction is hard in your brain. It's just like, well, because things has to go up and down, left and right, in and out, it's kind of tough. So most of the textbook will overlay the equivalent transverse oscillation with it, just like in a string, even though in the reality is a longitudinal wave. So this is part of the reason we said before, the mathematics that works for the transverse waves also work with the longitudinal wave. So that's why in terms of the visualization, if you are dealing with a longitudinal waves of sound, yeah, you can just overlay the transverse wave on top of it. It will behave the same way. So that's why we have the transverse description of waves on top of it. So let me introduce a second possibility of the oscillation. So you might be able to introduce higher frequency of sound inside the tube. As long as you treat the end of the tube to be a node, the open end to be an antinode, your job is done. Okay, make sense? All right, try it again. Yeah, I can do a higher frequency, and now you start to see a little bit better the oscillations that happening inside the tube, and then an equivalent transverse oscillation that you impose on top. All right, and now once you see this oscillating up and down, you look at it a little bit up and down, up and down, up and down, up and down, up and down. Then you switch to the textbook. Bam, right here. Yes. So when we multiplied by the time table, we swap places and we concluded that 2 times 10 is how we conclude that. Oh, how can we conclude that this is an amplitude? Okay, very good question. Actually, anything that shows up in front, oh, sorry, wrong one, down here. Yeah, anything that shows up in front of cosine or sine function will be amplitude. Anything, right? Back in the day, we only have like a capital A, right? We call that capital A an amplitude. But this time, we just have a bunch of things in the front. That's why the whole brackets there behave like an amplitude. Does that make sense? The whole thing, yes. Not the cos omega, the 2 sine kx, the bottom one, the last line. No, because I want the omega t to be in this position right here. The simple harmonic motion is the description as a function of time. So that's why I set the cosine omega t toward the end. And then whatever that shows up in the front will be treated as amplitude. It's a simple harmonic description. Okay. You might have to just cross-reference back in the day of the simple harmonic motion. Then you will see that whenever we try to describe a simple harmonic motion, we use a function of time, the omega t. Okay, make sense a bit? If not, then you just catch up later. We can describe a little bit more. But the idea is, oh, why don't we do this? Why don't you just flash back all the way? Have you tried that? You go all the way. All the way. Here we go. Oh, all the way. All the way. All the way. All the way. Here we go. It's a cosine omega t. Okay? All right, that was the description back in the day of the oscillation. All right, very good. So what we have there is, all right, guys, once again, let's take a look at this one more round. Stare at it. It's go up and down, up and down, up and down, up and down. And then when you come here, you are seeing that up and down thing, but it's more like a combined visual effects. There you go. So now I hope you understand this sort of like a visualization now. Okay, so that loop that you see over here, that is the transverse oscillations that sort of like we did overlay on top of the longitudinal waves to represent something that is oscillating in the tube. All right, so that's what it is. And we already knew that this is going to be a node, and this area right here is going to be antinode, node, and antinode. So everything that shows up right here is nothing more than it's just a wave oscillating up and down. But the representation in the textbook looks kind of, I don't know, it looks deceiving a little bit. It's not like a loop like this, because waves oscillate up and down so quickly. It might appear as a loop, okay, but it's not. Okay, so the best way to learn this, I think we're gonna try to do this together. And we are almost done because we already gone through those complicated sine and cosine function. So what I'm gonna do is, let me draw those closed air column, one end closed, one end open like this, 3 of them. Okay, and we already agreed that the closed end will represent a node for sure. That is a guarantee, because that is our restriction that air molecule cannot be moved. All right, and the open end will be treated as an empty node. There you go. So your job is just draw waves that satisfy these end conditions. Okay, that's all you need. For example, let's start with the easiest. I'm gonna go with the simplest one. All right, seems like something that might help. I love to draw a midpoint, or some sort of like draw a lines that separate the upper and the lower portion of the space. And then I'm gonna do this. I'm going like this, going from node to antinode. And usually I love to draw another line in the different type. So we don't want to kind of like stuck with the idea of a loop and anti-loop. It's just like a figure of a loop permanently. So it's just have it this, and I'm just gonna draw dot dash lines. That's the other half. That is done. That is the easiest possible wave that I can fit inside this tube. I can add one more twist to it as long as I start with the node and ends with the anti-node. So once again, I'm just gonna draw like a halfway point over here. And I'm gonna fit my waves in there, start from the node, ends with the anti-node. Right there, that's good. That's another possibility. Okay, or I can just twist one more. There you go. Nice. There you go. And you just keep going, and going. Okay, so you have more twists, and then you're gonna have shortened wavelength, higher frequency, fit into this tube. Okay, so that's why I said it seems like the process of get to the shape of the wave that fits into the tube is pretty much this. It's just you assign the nodes and antinode properly, draw proper waves that fits those restrictions. Your job is done. Okay, and this is a guarantee you will get a standing wave because there are nodes appearing. Those nodes position are the position where the oscillation does not occur. The amplitude of oscillation is 0. Okay, so what else can we do with this? Well, okay, John, if the tube has a length L, oh, now your job is almost done. I can trace back and figuring out what kind of frequency is it that is in that oscillations or in that mode. Look at the first one. If you try to sort of like extend the wave and, okay, I hope this helps, and come down. Oh, sorry. Come down here. 1 second. There. Yes. Questions?
What's the node and antinode?
The question about node and antinode is the one that we assign right here. The position where there are no amplitude of oscillation, we call it node. The position where the oscillation happens at the maximum amplitude, we call antinode. Okay, so that's why the left end of the tube will represent a node because we said the air molecule cannot move at all. Okay, and we go against that. I mean, opposite to that is the open ends of the tube has the freedom to move, so we assign it as an antinode. Okay, so when you look here inside the tube, it's only take a quarter of a wave. Can you see that? So I try to draw this. The yellow highlight over here, that's a quarter. The green is another quarter. The blue is another quarter. And the pink is another quarter. So that's why the region inside the tube, all right, I can erase this now. All right, that one's go. There you go. So I can say is the length of the tube is just a quarter of a wavelength. Yeah, inside the tube. And from that, that means my wavelength is 4 times the length of the tube. And now I'm using V equal to F lambda, so the frequency is just V over lambda. So I can just say the frequency is simply V over 4L. That is the way that I can figure out the frequency. Yeah, that's nice. Not bad. And you can play with it one more round if you want to. Okay, next one. You have that is half a loop, half a wavelength, and then another quarter. Okay, so with that, that means what you are having inside the tube is 3/4 of a lambda, and that fits the whole length of the tube. So the length of the tube is 3/4 the wavelength. So that means your wavelength is 4L over 3. And that leads to the frequency of 3V over 4L. And now you start to see like, hey, Dan, I can play this game. It's just like, you just extend this. There is a trend going on. So in the last one, you say, that's one complete wave and a quarter. So the last case, the bottom case right here is the length of the tube fits 5/4 of a lambda. So it's 1 full wavelength and a quarter. Okay. So that means your wavelength is 4L/5. And you can just calculate the frequency again, it's going to be 5V/4L. On and on and on. That's how you can figure out what are the possible frequency that it's going to generate standing waves in the tube. Nice. Okay, not bad, not bad. All right. The only thing that might sound bad later is just how would you like to distinguish between these cases? Sometimes people refer to this as mode. There are different mode of oscillation. Okay, there's some like a different modes. But the first one, the first type of oscillation is the simplest, the easiest, the lowest frequency possible. They call this fundamental frequency. This is a fundamental mode, fundamental frequency. There you go. All right. And just to be able to sort of like specify that, hey, this is the fundamental frequency, sometimes people just use subscript 1 right there. Or some textbook might use like F0, but to me, 1 is just very obvious. I kind of like it because it's saying, hey, it's the first frequency in this tube. Okay. And now when you move on to the next one, now you will be able to observe that, hey, Ajahn, is 3 times the fundamental. See that? So that means this one give you triple the frequency of the fundamental. So in the music terms, very much is the same thing. It's third harmonic. So this one is a third harmonic sound. It's a triple in frequency relative to the fundamental. And because it's 3 times the fundamental, you can put the subscript 3 underneath. Yeah, that's a simple one. That's kind of like easy to do. And now you can guess what should happen next. If you keep going, oh, Ajahn, I can see it now. The next one is 5 times the fundamental. Then, as you can guess, this is what I'm going to call fifth harmonic of sound. Okay, not bad. Not bad. All right. And then you can put subscript 5 into it. On and on. Now you can guess. The next mode is going to be the 7th harmonic, 9th harmonic. So that means when you are dealing with one end open, one end closed tube, you can only generate odd multiple of harmonic sound. Okay, that is the type of the tube that is going to generate. And sometimes because this generates some sound, so there might be like, we call it the tone of sound. So they might just call the fundamental, but sometimes they might refer to this as the first overtone. It's a tone that is over relative to the fundamental. And the second one that shows up beyond your fundamental, let's call it the second overtone, on and on and on. So there are 2 terminologies that is kind of like interchangeably used from time to time. But to me, the harmonic is the most obvious one because harmonic relates to the frequency directly. Okay, so that's, I think, the one that I'm going to try to stick with. But sometimes some textbook, I don't know, they use overtone from time to time because they only care about which modes beyond the fundamental. So it has some uses, depending on the situation. All right, sounds nice, not bad. It looks okay, right? It looks fine. So as I said, the end result is pretty nice. All you need to do is just draw a cartoon version of this oscillation and count the waves that you can fit into the tube. And the rest is simply just calculating the frequency. Okay, just so we are clear on what we are doing, shall we do the open end tube just so we have a full wrap of everything that we have here? All right, so let's come back here. I'm gonna do another page here, and hopefully you will see that this is gonna be straightforward from this point on. There you go. All right, guys, if you can do this together, would be nice. I fill this with 3 tube, but this time fully open. Okay, they are open end tube. And because of this, it means both ends gonna be antinode on both sides. because it's a location where things are free to oscillate. There you go. Okay. All right. And I once again draw a reference to be that's half the center of the tube a little bit. There you go. All right. So what I can do is first, let's look at the top one. I want to go from antinode to antinode. The simplest configuration will be like that. Oh, it doesn't go. Sorry. Sorry. The sound effect is already there, but the figure is not yet. It's bad. Okay, here we go. Let's hopefully it's not bad. And then I love to just do the other one as a dash line. There you go. That's the simplest possible. All right, but then you can add one more twist to it if you want to. Okay. There you go. So that is the next mode of the standing wave that you can generate here. And of course, one more twist. Here we go. Nice. On and on and on. Okay, you just keep drawing, drawing, drawing. Let's start from the top. That's the simplest one. If you look at it, that's half of a wave. Because if you connect the rest of this one, that's another half. So what you can say is, oh, in this case, the length of the tube is half of a wavelength. So that means the wavelength is just twice the length of the tube. And the frequency that you're going to get is just the speed divided by wavelength. Done. Okay, all right, not bad. And that you can guess as well. We call this fundamental frequency. Nice. And then you can put subscript 1 for it. That is your lowest possible frequency that will get generated in this type of tube. Okay, move on. Let's go higher frequency, next mode. So what you can count is full wave, one full wave. So that means in this case, length of the tube is one perfect wavelength. So the lambda is L. So your frequency is just V over L. But we kind of know the trick. We want to know what is this frequency relative to the fundamental frequency. I can multiply by 2 divided by 2. So I can recognize that V over 2L is our fundamental frequency. So this time, your frequency in this mode is twice the frequency of the fundamental. So you can just call this second harmonic. Nice. Or you know it, this is your first overtone. It's the next tone that is over from the fundamental. Yeah, nice. Okay. But now you start to see a trend here, because if you move on to the next one, that's one full wave, another half. So what you have here is your length of the tube is 3 lambda over 2. That means your wavelength is 2L over 3. And the frequency is just V over 2L. I flip 3 to the top. And you can guess that, of course, it's triple the fundamental frequency. So this one will be named the third harmonic. You can refer to this mode as a third harmonic, which is only the second overtone for this type of tube. And you can see the trend for the rest of this whole standing wave inside the air column. Okay, so you can call this a tube. You can call this an air column. You can call this, I don't know, what else would it be? Yeah, but usually they refer to this as like I don't know, a sonic tube or organ pipe, anything that has like a channel of air that it can fit in. You can use this configuration to fit the wave inside that tube all the time. Okay, makes sense a bit at this point. Not bad. All right, so hopefully you see the whole point that I'm saying, that toward the end, this whole formula hopefully is clear to you, even though the description is just, we do it kind of like real time a little bit. But the good news, because in the exam, you are allowed to bring in a one-sided A4 note. You don't have to do anything. You can just put this figure on it if you want to. You can just draw all the formulas. I mean, write down all the formulas, draw all the figure, bam, put it there. Simple, right? You don't even have to draw it yourself. So easy, right? Hopefully it helps a lot. All right, sounds good? All right, so let's stop right here. And we will do an exercise after the break. Sounds good? All right, so have this thing sit in your brain a little bit. So make it kind of like mature in your brain. All right, let me stop my video for now and pause it first. But before we get to that, I hope this will remind you of standing wave at all time, every time that now you drink a cup of coffee. Here we go. So straw actually is an open end tube, okay? So you can generate sound. That is a frequency coming out of it, all right? And of course, if you dip this into a cup of water or coffee, then this will be different frequency. And then if you adjust the height, it's gonna depending on the column of air above the water level. Okay, so you can adjust the height of it, and then frequency will reflect what you're seeing over here. It's right here, right? Something like that. Okay, and that is kind of like normal for any wind instrument. It uses something like this at all time. And now you probably will understand from this point on that every time that you hear sound coming out from a bottle of water and you try to fill water with it, then you hear the sound coming, yeah. So you hear that it starts from a low pitch sound, and then you go. That's higher pitch. The reason for that, now you understand, it's because of this. When you fill water, the water level rising, and that decrease the length of the air column above the surface water, the water surface. So you have a shorter and shorter and shorter tube of air. So that's why frequency shifts to a higher frequency. Okay, makes sense? All right. So that is standing wave that happens. But there are some textbooks that also refer to this phenomena as a resonance. Oh, all right. Just in case, we're not going to dive too much deeper into resonance anymore. Okay, but that is another term that somehow is just the same for waves in an air column. It happens at the same time. The resonance is just the effect that sometimes you enhance the oscillation by having an external exciter or something that's kind of like have an excitation, a force. There is some extra term that get into it to make things move a little bit more and more and more violent in times. That is a resonance effect. This is part of it, all right? But it just kind of confuse you more if you try to get into why this one called also resonance. So let's stick with the standing wave. I think that's kind of like okay for us. All right. So you will see how easy it is for you to solve this problem. And it seems like it's like another 5 points that you can collect from the exam one. It's a guarantee that this topic will show up in the exam. A section of a drainage covered 1.23 meter in length makes a howling noise. So now it's no doubt, every time you go into a tunnel, you have this kind of like a drainage, a tube or anything, that is a sound all the time, every time air blow across it, because that is a standing wave coming in from that tube. So the wind blows, generate howling noise, determine the frequency of the first three harmonics of sound, that if you treat this as an open-end tube. Oh, all right, Adan, there's an open end. Okay, if you want the first three, you can just draw this three. But if you want, I can just quickly draw this diagram. Okay, but of course you can refer to the formulas or the figures in the previous page. And then you can just say right away, oh, if this tube has the length L, okay, so that means what you have, oh, why I cannot draw, you know, there. All right, and the length of the tube is just lambda over 2. Yeah, okay. And we already did this. So the lambda is twice the length. And the frequency is going to be V over 2L. And because the speed of sound is already given, the length of the tube is also given, I can just substitute those numbers in. There you go. 1.23 meter. Bam, right there. Done. When you say done, this is your fundamental frequency. The lowest frequency possible, you might just put subscript 1 to it. Just say, hey, this is fundamental. But now you don't even have to do anything else if you don't want to draw anything anymore, because you know that for open-end tube, you can generate all harmonic of sound, right? So if you refer back to this, there you go. Yeah, it's possible to create second harmonic, third harmonic, fourth harmonic, on and on and on. So that means I can just say the next one is going to be twice the fundamental. The third one is going to be triple the fundamental. My job is done. Okay, because you already know the nature of this type of tube. So you can just refer to that properties and be done with. Okay, not bad, pretty good. And same thing will happen if the next question say, hey, it turns out it get blocked at one end of the tube. No big deal. So now you turn into the situation of one end open, one end closed tube. Okay, and if you want to draw a little bit just for fun, yeah, that's fine. Let's go like this. Come down like that. And you remember or can refer to the length of the tube is a quarter of a wavelength. So the wavelength is 4 times the length of the tube, and the frequency is V over 4L. That is your fundamental frequency. And because this is an one end closed, one end open tube, you know you can only generate odd multiple harmonic. Yeah. So you can just tell the next one is going to be F3, triple the fundamental, and the next one is going to be F5, 5 times the fundamentals. Your job is also done. Okay, so I think this portion of the questions is just a matter of if you kind of like, you know, get to understand this property a little bit, but I didn't want to dig into the trigonometry of it or mathematical description of it. So toward the end, it's just a matter of you know how to fit waves in the proper way. When I say proper ways, now you understand the closed end has to be a node. The open end is going to be an antinode. And as long as you satisfy these ends conditions, you can figure out the frequency through the wavelength in the tube. Okay, guys, not bad. All right, so hopefully this is another 5 points for you to pick. And don't worry, before the exam, I will list exactly how many questions and what type of questions is going to show up. So you can expect what going to get asked. Like number 1 is oscillation, number 2 is waves description, number 4 is like, so you know what to expect. Exactly. All right. So we call it done for sound. Okay. So we still have time to introduce another kind of waves. It's called lights. But we only care about the optics. So that will be the part that we're going to end today. So with is, let's study 2 properties of optics. One is called reflection, the one that you're probably familiar with the most. Every time that waves hit something, it reflects back. So that's not big of a deal. The one that is going to pretty much need a little bit of calculations is called refraction. The refraction is a bending of waves. And because we are talking about light, so we can just say bending of light, but in reality, any waves can refract. So, but we just use light as our mean of study. All right, so we're gonna attack these 2 things and we call it done for today. Not bad, right? You will see that it's not bad at all. But the things about these topics is this. I will not go back to talk about the interference. We're not gonna go back to use sine and cosine function. We're not gonna deal with any analytical things anymore because that's already done. What we are going to do is we're going to just look at how light is traveling. Okay, so that means I can just use directions or lines and arrows to represent its motion. And it can bend, it can change direction, it can reflect anything, but it's still among those lines. So the lines that represent the traveling direction of light, we call it the light rays. Okay, this is okay, all right? This terminology is not bad. The ray of light is right here. However, the good things about this one is you only need geometry to deal with this because you only care about which way it goes, which angle it makes with that, what kind of reflection is going to get on and on and on. So this part of physics we call geometric optics. It's an optics that only require geometry to analyze. Oh, that's going to be fun and not too complicated. So I think it's a good stop before we call it done for the first unit. All right, right here. So the first property is the reflection. Everyone knows reflection. All right, but what we're going to do in here is the reflection in 2 dimensions. We might have seen a 1-dimensional reflection before, you just go back, right? If you go forward, you get reflected, you just go backward. But if it is a 2-dimension, you need an angle. And from this point on, every time that you are talking about an angle, that angle is an angle that is measured with respect to a normal line. You have to somehow draw a normal line, a line that is perpendicular to the surface that things is about to happen. And most of the time, the angle in any formulas is the angle that is referred relative to this normal line. Okay, so that's the way that we agree to do this. It's convenient for, I mean, further away when you do something else, then you agree that having a normal line is convenient than refer to just the surface of the material itself. Okay, so in this case, the theta 1 will be an incident angle. And of course, if you just get a reflection, everything will be just like a mirror image. So you're going to get a theta 1 prime to be a reflected angle. And the law of reflection is super simple. Theta 1 equal to theta 1 prime. Your job is done. Okay, the angle of incidence is the same as the angle of reflection. But this property actually built into the matter of how smooth your surface is in that reflection. For example, if you have a pretty smooth surface, every point on the surface gets the same type and same angle of reflection. So it can, think of it this way, it can retain the information on the way in toward on the way out, right? It looks good on the way out as on the way in. So that's why you can see a reflection from a smooth, glossy surface. Like, well, whiteboard is pretty, yeah, it's not super glossy, but you can still see a faint reflection of it. So the information that gets reflected is still being retained on the way out. But on the other hand, if your surface is super duper rough, so the reflection goes on every point. The law of reflection stays. However, it seems like you are losing all those information. So we call this a diffuse. Your information get diffused out. So it's a diffuse reflection, and this will appear matte to you. So that is a matte finish. That's what it is. So the ceiling, for example, or of course, if you want to do your makeup and you want to have your face look a little matte, then those powder will create a rough surface. So it's diffuse the light out. So you have a little bit of no reflection there. Okay. All right. So that is kind of like an application that happens all the time. And the distinguish that can happen every time that you just consider the surface smoothness. So that's not bad. All right. But we're just going to pass on this one because not much to it. Just reflection is simple. In equal to out, your job is done. The one that is more interesting is this one. And this is going to be the key equation for the day. We call it the bending of light. It's called refraction. This is the one. So it can reflect and it also can refract. So these terms state that whenever light tries to go from one medium, like this one in air, and it has to enter another medium, then there could be a change in the traveling direction of light. That is the bending of light. Okay? And because there is a change in the direction, the angle comes into play again. Right here. Once again, normal line is drawn right there. You have a normal line. Perfect. That's good. All right. And the incident angle is theta 1. measured with respect to the normal line. And the theta 2 that come out, the refracted angle, also measured relative to the normal. Perfect. All right. And the way that we can calculate the relationship between these two angles is through an equation called Snell's law. We're going to use this equation to link between the theta 1 and theta 2. And the shape of the equation looks like this, guys. I don't know, have you seen this from high school, but some of you might have seen this already. N1 sine theta 1 equal to N2 sine theta 2. Or just saying the product between the N value, which I'm going to explain what it is, and the sine of an angle stays constant at all medium. Okay? What is N then, Ajahn? It turns out the definition of N is the following. We define N as the ratio between the speed of light in vacuum, which everyone knows this is the largest possible speed in our universe. Every time I talk about this number, it's kind of weird, right? That's nothing can move faster than the speed of light. So that is the largest number for anything that is moving. Amazing. Divided by the speed of light in that vacuum. And everyone can guess because nothing can travel faster than speed of light in vacuum. So this N must be greater than 1 at all time, right? Because anything that's not light in vacuum will move more slowly than that. So that is a guarantee that this definitely either greater or equal to 1. So let's take a look at some common material. So the vacuum, the N is 1. Okay. The proper name of this one, we call the index of refraction. That is the N. Or sometimes they might just say a refractive index. But because it's so commonly used that N can be understood. You can say N of something, N of water, N of glass, N of diamond. Yeah, everyone understand N means index of refraction. So that's pretty good right there. So with this, then the vacuum is 1. The air actually is, yeah, you can approximate it to be 1 because not a lot of air molecules in the way. So light can still pretty much goes on easily. But once you hit water, oh, now you have some effects there. It's about 30-something%. And glass is about 1.5. The higher the density, it seems like light having a harder time going through. Sapphire, the ones on maybe your Apple Watch and all this stuff, that's 1.77. Okay, and the ultimate one, the diamond, is 2.4. So that means light travel very slowly in diamond. But this to be expected because everyone knows diamond is super dense, right? It's kind of tons of carbon atoms in it. So light has to interact with all those electrons and atoms and everything before it can get through. So that's why it's moved more slowly, all right, in mediums. All right, so it's good to know. So once you know what N's are, that's it. N of the first medium times the sine theta inside that medium must stay fixed at all times. This is Snell's law. All right, some textbook might just want to spread this Snell's law out in different form. That is okay, but it's just a ratio. So don't worry about it that much because you can always turn N into either speed or the wavelength if you want to at any time. So that we can practice this in the exercises, but for a simple form of the Snell's law, most of the textbook stick with the N1 sine theta 1 equal to N2 sine theta 2. That is just, I don't know, just convention, I guess. All right, let's take a look what kind of question that you can show up. But no matter what questions it could be, you will end up with either one of these two. You have no choice. Look at the first one. You're going from air to glass. I can now write down the value because everyone kind of have seen the table already. So let's say if I call the air to be subscript A, so N sub A is 1. Glass, let me call it the G. N sub G is 1.5 approximately. So you are going from smaller N to a larger N. So the angle will go oppositely. Everyone with me? So when N is small, and you try to go to a larger N, the angle will go from a bigger one to a smaller one, right? Because from the Snell's law. So in that case, the bending will be towards the normal. On the other hand, if you have an opposite case, when you have light coming from a bigger N to a smaller one, then it will go opposite. light will try to bend away from the normal lines. Yeah, that's pretty good. But then that's it. You can either have one of the two, right? Either bending towards the normal, or you try to be more straight up, or you try to bend away from the normal, and you try to be, spreading out. Yeah. All right, you want to give it a shot and see how it goes? All right, here we go, guys. Try a simple one. You have a ray of light strike a flat block of glass. So you have glass block. And then, okay, let me draw those as lines right there. There you go. Okay, that's a block of glass. Okay, and of course, I can always love to draw a normal line. So like that. And there is light that hits at the angle of 30 degrees, bam, from the top right there. Okay, and this block of glass is given N to be 1.5. And on top of glass is air, and underneath glass is also air. So I can just signify the value of N of each medium properly like that. N of air equal to 1, N of glass 1.5. Okay, so what should happen then? From the look of it, Ajahn, the incident angle is given to be 30 degrees. Okay, and because you're going from N equal to 1 to N equal to 1.5, the angle will be smaller. So that means the first refraction will go like this. Everyone with me? So it will bend towards the normal. All right, and then it's gonna hit the bottom surface. So you will have to do another refraction down here. Once again, I draw a normal line. And because this time it will go oppositely, because now you're coming from 1.5 to 1, your angle will go bigger on the way out. So this is the whole situation that is happening when you have to go through different mediums. Okay, not bad. All right, so with this, then now your job starts right here. Every time that you want to apply Snell's law, don't think too much, because we are doing a geometric optics. We're doing rays. You only apply Snell's law at the point that things are happening. Like this one is a point of refraction. What does it mean? It means I only have to focus on, for example, let me name this point A. Let me name this point B. I only care what is going on one point at a time. So I can say at A, there we go, that's a top surface point. You can just say, oh, okay, that is right light coming in, light going out. I can just name the outgoing ray to be alpha. This is angle right here. Okay. So if that is the case, at point A, I can just say NA sine 30, everyone with me? That is happening in the air, must be equal to N of glass sine of alpha. And that's it. That's how you apply Snell's law at point A. Your job is almost done. Then I can substitute the value. N of air is 1. Sine 30 half. N glass 1.5. No big deal. So now alpha can be found using your calculator. Okay? Easy as that. All right. So Snell's law is good, compact, easy to use, not very confusing. All right. And then you move on to point B. And then you try to do geometry. Well, Ajahn, actually for this problem, it's still pretty good, because if the red angle right there is alpha, I know this is going to be my opposite angle. This is also alpha. Okay. And if I want to figure out what should be my outgoing angle underneath. Let me name beta. So I apply Snell's law at point B, doing the same thing. You can do in any order you want. It doesn't matter. I can start from the glass. N glass sine alpha must be equal to N air. It comes out to air, and then sine beta. See, your job is done. Okay, but one thing about this one is, well, John, wait a second. They look the same. Look at this. N glass sine alpha shows up right here. And NA, end of air, shows up here as well. So as you expected, you don't even have to calculate. Everything just trace back. The beta must be 30. Okay. The reason is because on the way in at point A and on the way out at point B, it's just like things just go reverse of each other. And that is perfect because Snell's law has no direction. It doesn't tell you that the light has to travel from what to what. So it's kind of like makes sense that these two equations look exactly the same, because if you were to go backward in time, which is, of course you cannot, but let's say it doesn't matter if you shine the laser light from the top surface down, or you want to go backward, you want to shine the laser light from the bottom of the glass up, it will follow the exact same path. Okay, it doesn't have any preferred direction. Okay. Light go in a straight line, forward and back, same thing. Okay, that's nice. All right, so hopefully this gives you a sense of what is about to happen. So things are, I would say, good, not bad, not bad. All right, so if you are okay with this, I would like to go, okay, let me do one more. Let me cross the second exercise and go through the third one because it's so easy. Yeah, so if you want, you can skip the second one first because we're going to use it as our final exercise. But if you skip forward to the third one, it will look exactly the same, except the bottom layer is not air. It's just the third material. But do you care? You do not care. Everything will work exactly just like this one. Okay. So what we can try to do is, here we go. Oh, Adan, you have air on top, you have oil in the middle and the water in the bottom. This is exactly what happened when you spill oil on water. The oil is just sort of like stay on top and at the layer on top of the water surfaces. And that is something that is really happens here. So the light hit the top surface, go through the oil layer and try to enter water. What do you worry about? Nothing at all, because look at this. Look at this point first. Let me name this point A. You already got all of the information needed to figure out the theta prime. Can you see that? All right, I can write down right away at point A. Start from the oil, N oil. Let me call this N sub O. And then you use 20 degree, sine 20 degree, equal to, now you come down to water. Let me name this NW, N of water, and then you do sine theta prime. Because you know all of the value of the N's, because it's already been given that oil has an refractive index of 1.5. So it's 1.5 sine 20. In water is 1.33 approximately from the table. There you go. Theta prime is done. Yeah, something like this. Okay, not too bad. You only apply Snell's law at a point of refraction. So once again, same geometry. But I can see it. If this is 20, this must be 20 as well. The opposite angle. So you can now go up here, look at point B. And you do the same thing. All right, well, at B, oh, you can start from the top, NA up there. So NA sine theta must be equal to N oil sine 20. And that's it. From here, the theta can be found. Okay, you can call NA is 1, N oil is 1.5, sine 20 is just calculator, and that's it. Okay, so just to reaffirm that Snell's law is only applied at point of refraction. That's it. Okay, and then if you can figure out the angle of incident or refracted angle you want, or whatever the unknown left, is just use Snell's law this way. Okay, everyone seems to be not bad, right? This is kind of nice. All right, this is not bad. So last one of the day, guys. Let's be more realistic. Something that is actually happens might be something like this exercise. So now you have a rectangular metal tank. It's filled to the top with an unknown liquid. You have an observer with the eye level with the top of the tank. Oh, okay, okay. There you go. All right. So you have somebody observing, leveling his eyes at the surface of the water. Now, a ray that refracts through toward the observer is at the top of the liquid. The dimensions of the tank is given, the length of the tank, the depth of the tank is there. What is the reflection index of the liquid? Ah, you want to try this? So this one is not bad. It looks, even though not perfectly realistic, but this is the one that you can observe daily if you want to try to look at the bottom of any water tank. You will feel that the bottom of the tank gets shallower, right? You feel that. And that is because of the refraction. And because your brain cannot do anything else, any light that hits the eyes, your brain says the object is in the front at all times. So that's why this time the image of the corner of the tank gets up here, refract to your eyes will see it just like it comes from the front. So too bad. That's why you can still see the corner of the tank this way. All right. So how do we do this, guys? Want to try? 10,000 points. Just kidding. All right. A different kind of point. So, all right. Think in the manner of refractions must be happening at some point. And that point is, let me mark right here. See, the refraction happens here. Okay. So if that is the case, then the normal line must be drawn and it's already there. That's good. So there is a normal line right there ready for you. So now your incident angle is this dude right here. Let's call it the theta. Okay. And the outgoing, the refracted angle is perfect. It's 90 degrees because they assume that the ray that come out of it go horizontally. So once you get those two angles set, use Snell's law. Let me name this point A again. So at A, all right, you can start at any point. You can start from the top or you can start from the liquid, doesn't matter. So what you get is end of air, sine 90 degree, that's the air medium, equal to, now you come down to the end of the liquid. So I'm just gonna write the whole thing down, end of the liquid, and then sine of the theta. And then when you look at this, wait a second, you already know what the theta should be because you know the dimension of this. So if I pull this triangle out, there, right there, let me draw it on the side here. That's a triangle. So what you have here is your theta is coming from 80 and 60. Yes. Come again? Oh, because if you look at the ray that coming out is horizontal. But every time that we want to calculate the angle or put the angle into our formula, it must be relative to the normal. Normal is normal to the surface of the water. So it's go vertical at this point. Yeah, normal line. Yeah, it's a normal. Up, up, go up. So the red line is making a 90 degree with the normal line. Oh. Okay. All right. So with this, then this angle can be found. 60 is not that position right there. Sorry, guys. So 60 is here. There you go. So from here, some of you have already probably observed this is like that is a 3, 4, 5 if you want to. Yeah. Is that right? I think so. Yeah. All right. So the theta can be found no matter what. That's what it is. All right. So with that, I can substitute value. End of air is 1. Sine 90 is 1. And liquid, this is what you want to figure out. And sine theta is 80 over 100. Here we go. And that's it. End of the liquid that we were looking for is just 10 over 8. And then you can just 1.125. Done. Nice. Is that 1.25 or 1.125? 1.25, sorry. Just extra 1, that's too much. There you go. 25. There you go. All right, not bad. Okay, guys, so that is it for today. And next time, we're going to look at some extra phenomena that can be sort of like built upon knowing what the Snell's law is, what is happening to the refraction, and then we're going to look at the total internal reflection. And we will end this unit with image formation, and we call it done. Sounds good? All right, guys. So one more lecture to go on Thursday, and we call it complete of the unit 1. All right, guys. Have a good day. I'll see you on Thursday.